In the last couple of segments, we looked at the different conformers of cyclohexane and cyclohexane derivatives. Those were structures that we could arise at, three-dimensional shapes, that arose by just rotating around carbon-carbon bonds. In this unit, what we're going to look at are what we refer to as the cis-trans stereoisomers, or the cis-trans stereochemistry of cyclohexane derivatives. Cis and trans refer to the orientation of two groups on the molecule relative to one another. And we're going to use as our example to introduce this concept of cis-trans stereoisomers the molecules up top that represent 1-ethyl-2-tert-butyl cyclohexane and the ring-flipped version of that molecule. When we talk about the term stereochemistry, what we're referring to is two molecules that share the same connectivity between atoms, meaning they are not different constitutional isomers. They have the same branches coming off the molecule at the same positions, like, for example, a branch coming off at carbon number 1 of the ring and a branch coming off at carbon number 2 of the ring, but they have a difference in their three-dimensional shape. So the different conformers that we've talked about in the previous unit would be examples of stereoisomers, or molecules that have different stereochemistry. They have differences in their three-dimensional shape. Another example of stereoisomerism is the definitions of cis and trans. When we describe a molecule as being cis, what we're referring to is that two groups of interest that we're focusing on are on the same face of the molecule, meaning that they are both oriented upward relative to the carbon atoms of the ring, or they're both oriented downward relative to the carbon atoms of the ring. They're either on the top, both on the top face of the molecule, we could say, or both on the bottom face of the molecule. In other words, if we were looking at the carbon atoms of the ring, what we would see is that both of the groups of interest are either above the carbon they're bonded to, or both of them are below the carbon they're bonded to. On the other hand, trans is the opposite of cis. Trans means different, and that means that the two groups are going to be on different faces of the molecule, or opposite faces of the molecule. In other words, one of the groups is going to be located above the carbon it's bonded to, and the other group is going to be located below the carbon it's bonded to, in order to describe the two groups as being trans to one another. So what we're going to look at is the example problem up top here, and we're going to try to assign whether each of these two molecules is cis or trans in terms of where the tert-butyl group is located relative to the ethyl group. So let's take a look. We're going to take a look at the carbon atom here of the ring as our frame of reference. I'm highlighting that in green. And we ask ourselves, is the tert-butyl group going to be on the top face of the molecule or the bottom face of the molecule? In other words, does it point up relative to the carbon atom that's bonded to, meaning it's on the top face, or does it point downward, meaning it's on the bottom face of the molecule? So we look at that carbon atom, and that carbon atom is definitely located above the tert-butyl group. We have to go downward just a little bit to get to the tert-butyl group. So we would describe the tert-butyl group as being oriented downward relative to the carbon atom that it is bonded to. We could also describe that group as being equatorial, but I'm not going to label it as equatorial here because the assignment of axial and equatorial does not have anything to do with whether two groups are cis or trans to one another. You could have two groups that are both axial that are trans, two groups that are both axial that are cis. We need to look to define cis and trans as how is the group located relative to the carbon atom that's bonded to, not really using axial and equatorial as a reliable way to assign that. So we've assigned our first group there, our tert-butyl group, as being down relative to the carbon atom it's bonded to. We need to come to the next carbon atom here and look at our group, our ethyl group, and that's definitely located down below the carbon that it's bonded to. So I'm going to go ahead and label that as down as well. And therefore, since both of these groups are on the same face of the molecule, they're both pointed downward relative to the carbon that they're bonded to, we would describe this molecule as being cis, or same, meaning those two groups are on the same face of the molecule. We then do the ring flip of this molecule. We look at the structure in the upper right, and we can ask ourselves the question again, is the stereoisomer that we see up top here on the right described as cis or trans? In other words, the broader question that we're asking here is, by doing a ring flip, are we able to change trans to cis or cis to trans? Or when we do a ring flip, does the cis-trans stereochemistry stay the same? So we have to ask ourselves the question here for our ring flipped version that we've drawn of whether the two groups that are bonded to the ring are both oriented up, both oriented down, or one's up and one's down. So let's take a look first at the tert-butyl group. Here's the carbon atom of our ring, and we're definitely going downward to get to that tert-butyl group. So I'm going to go ahead and label that as down. We come to our bond to the ethyl group. Ethyl group bond is down below the carbon atom of the ring. So I'm going to label that as down. So what you'll notice here is that the structure that we finished off with after the ring flip is still cis. So this brings us to a really important point about this cis-trans stereochemistry, and that is doing a ring flip is never going to change cis to trans or trans to cis. So ring flips do not alter cis-trans stereochemistry. A molecule that starts off as cis, if it undergoes a ring flip or 20 ring flips, will still be cis at the end. So ring flips never change cis-trans stereochemistry. They just change the conformation. So they never change cis-trans stereochemistry. And there's very few things in organic chemistry that I throw out here as an absolute never, but ring flips are one of those things that will never change cis-trans stereochemistry. In most cases, when we talk about organic chemistry rules, there are exceptions to the rule, but this is something for which I know of no exception. When we rotate around carbon-carbon bonds to go from one ring to the flipped version, we are not going to change the cis-trans stereochemistry. A molecule that starts off its life as cis will continue to be cis unless the only exception is if there's an actual chemical reaction. In other words, we break a bond that's cis and we remake that bond as a trans bond. That's the only way. That's a chemical process that allows that to take place. A ring flip instead is just a physical process of rotating around carbon-carbon bonds. So whenever we look at a molecule and we're relating a structure to its ring flipped version, one way to tell whether we've correctly drawn the ring flipped version or not is to look at and assign the two structures as cis or trans. If they are both cis or both trans, that suggests to us that we've done the ring flip correctly. On the other hand, if we notice that we've changed a cis molecule to a trans molecule by doing a ring flip, that is a never-never rule. So it means that you've drawn something wrong along the way. So next up, let's take a look at a couple of example problems of how we can apply this information of cis-trans and relate it to the energies of the different conformations of cyclohexane derivatives. We'll tackle this example problem where we're going to draw two conformers, meaning chair conformations, of trans 1-bromo-3-ethyl cyclohexane. And we're going to ask which of those conformers would be more abundant if we had a container of trans 1-bromo-3-ethyl cyclohexane. So I would encourage you here to hit the pause button. Try to draw out yourself those two different conformers of trans 1-bromo-3-ethyl cyclohexane, and then we'll go from there to see whether you got that right or not. So, looking at the solution to this problem, what we're going to do, drawing the two chair conformers of trans 1-bromo-3-ethyl cyclohexane, we need to be able to make our chair flipped versions of this. So I'm going to start by drawing one of the two conformers of this molecule. And we could draw these in either order, by the way. It doesn't matter which one you draw first and which one you draw second. So I'm just going to draw one of these out, draw in my axial and equatorial bonds, and make sure that I'm drawing this molecule as trans 1-bromo-3-ethyl cyclohexane. And we can take shortcuts along the way here and leaving out the hydrogens if we want. Another common thing that you'll see is that these bonds here in front are highlighted or wedged in order to make it evident that these are the ones that are forward, that are furthest forward in front in the molecule, hence bold. So trans 1-bromo-3-ethyl cyclohexane, we're going to draw the two conformers of that. And we need to absolutely make sure that those are trans. So I'm going to put in the upper right corner here my position number 1 of my ring. And I'm going to go ahead and plug in my bromine group there. So my bromine group at position 1 could be either axial or equatorial. I'm just going to arbitrarily put it as axial. At this point, it doesn't matter which one you put, whether you put this as axial or equatorial. So I've put it as axial, but you could have put it as equatorial too, and that would have been correct as well. So at position 1, we have our bromine group. Then we come over to position 3. So I'm just going to go number 1, 2, 3. And at position 3, we have our ethyl group. So I'm going to go ahead and fill in our ethyl group. And it is important where we put the ethyl group, axial or equatorial, because that's going to dictate, based on whether the group is oriented upward or downward relative to the carbon it's on, whether we have drawn the cis or trans molecule. So we have two options for where we can put the ethyl group. We could either put the ethyl group pointed upward like this, and that bond at that particular location would be described as axial, or we could put it right here, going downward relative to the carbon it's on. So which would we want to do here? For purposes of keeping in mind that this is the trans version, we put our first bromine group in the upward position above the carbon atom that's bonded to. So therefore, at position 3, the group we plug in needs to be below the carbon atom that's bonded to. In order for these to be trans, the two groups have to be on opposite faces. So I'm going to go ahead and fill in the bottom line here with my ethyl group CH2CH3. And I'm going to go back and erase that bond that I've shown there, axial, since we're drawing kind of an abbreviated form of this molecule, not showing the hydrogen atoms in here. Therefore, I don't really need that line. I'm just showing the groups that are actually present. And these two groups that we've shown would certainly be trans to one another because the bromine group we pointed upward relative to the carbon it was on, and the ethyl group we pointed downward relative to the carbon atom that was bonded to. So one's up, one's down. Now let's draw the ring-flipped version of this molecule. So we'll go ahead and draw our equilibrium arrow, because at equilibrium in a container of this substance, both of these rings flip the rings, both of these chair conformations would certainly exist. Our job here is going to be to determine which of these two is more abundant based on the relative energies of them. So in order to assign that, what I'm doing is going ahead and drawing the ring-flipped version of this molecule, and then we're going to compare the two structures. So our ring-flipped version, I'm going to take our bromine that was at position 1, put it right here in the lower right corner, and then numbering around the ring clockwise, 1, 2, 3. So at position number 1, our bromine group that was axial to start with, by doing a ring flip, will always become equatorial. So at position 1, bromine needs to be equatorial. At position number 3, our group that was equatorial to start with needs to become axial. And I'm going to put it as axial, pointed downwards, CH2, CH3, because that's what would be the case at this particular spot. And it's totally okay if you need to draw in all of those axial and equatorial bonds in order to get correct that this is going downward. You can totally do that. I'm just making an abbreviated structure here. The other thing I'm going to do is I'm going to fill these bonds here that are in front in as wedges, just so I'm consistent with the structure I drew on the left there. And now that I've drawn this out, we can assign this structure on the right as cis or trans, and we should find that it is still trans. Doing a ring flip will never change between the cis and trans forms of a molecule. And indeed, we find that this molecule is still trans because the bromine is up now relative to the carbon atom that's bonded to. So that bromine is up, and the ethyl group is down. Therefore, those two groups are still on opposite faces of the molecule, so both of these molecules would be described as trans. So this represents the two different trans conformations of this molecule. The conformations we arise out by doing the ring flips to go from one to the other, where we switch all the axial groups to equatorial and vice versa. Switching axial to equatorial is not going to change trans to cis, however, so our trans molecule to start with should stay trans at the end. Now we ask the question, which of these is more abundant in a container? So in order to assess which is more abundant in a container, we keep in mind that the favorable conformation is going to be the one that has the bulkiest group or groups in equatorial positions. So more abundant, we want to put bulky groups equatorial because that gives them more room to roam. So looking at these, we would expect the ethyl group to be bulkier than a bromine atom because a bromine atom is just one atom. The ethyl group is multiple carbon atoms, which are relatively large. So we want to make sure that that ethyl group is equatorial. And it is only in the structure on the left where our ethyl group is equatorial. In the structure on the right, the ethyl group becomes axial. So the structure that is going to be lower in energy is certainly going to be the structure on the left. The fact that it is lower in energy, or in other words, more stable, means that it is going to be the more abundant conformer. Molecules prefer to be in the lowest possible energy, much like I generally prefer to be in the lowest possible energy. So this is going to be your more abundant of the two conformers. Now we can take this a step further And we can ask ourselves to draw the two conformers of cis 1-bromo-3-ethyl cyclohexane and ask of those two structures which is going to be more abundant within a container. So what I'm going to do is come down here below and add to this problem by drawing. I'm going to add to this problem by drawing the same problem here, draw two conformers, except we're going to do cis this time. Not trans, we're doing cis, they can't be both. Cis 1-bromo-3-ethyl cyclohexane. And we're going to ask which of those two molecules would be more abundant in a container. So we'll go ahead and get started here by drawing out our template. So we draw the template in, following those guidelines from the earlier video about drawing chair conformers of cyclohexane. At position 1, we're going to put in a bromine group, and that bromine can be oriented either axial or equatorial, it doesn't matter which. I'm going to go ahead and just put it into the axial position for fun here. And that's carbon number 1. Coming on over to carbon number 3, we have to put in our ethyl group. And in order to be sure that this is cis, we need to make sure that both of the groups are on the same face of the molecule. The bromine was oriented up relative to the carbon atom that it was on, so therefore the ethyl group also needs to be oriented up relative to the carbon atom that it is on. And at position 3, if we were to draw out all the bonds here, we would see that the axial groups are what is going to point up there. So we go ahead and put in our ethyl group CH2, CH3 to give us 1-bromo-3-ethyl cyclohexane as the cis configuration, the cis stereoisomer. So we've got that drawn. Both of those groups are pointed up, meaning same. They are on the same face of the molecule. Now we're going to go ahead and do, for this molecule, the ring flipped of it. So we'll go ahead and do our ring flip. And I'm going to draw out the ring flipped stereoisomer of this molecule. Just drawing in my bonds, following the template for drawing these chair conformers. I'm going to put in the lower right-hand corner my bromine group now. And in doing a ring flip, remember that all axial groups become equatorial and vice versa. So our bromine started off on the left bottom as axial. So now it needs to be equatorial. So I'll go ahead and plug in the bromine as equatorial. At that position, the equatorial group is on the top face of the molecule. It's angled slightly up. Then we come on over to carbon 2 and carbon 3. Our ethyl group started off on the lower left as axial. Therefore, in doing a ring flip, it needs to become equatorial at position 3. And at position 3, our equatorial group is going to be oriented slightly up. So I'm going to plug in my CH2, CH3 there. And now we should always ask ourselves, once we've done the ring flip, have we made the cis configuration, and a cis stayed cis in doing this ring flip. So we started off with cis definitely because both of the groups were both up relative to the carbon atom they were bonded to. We finished off with a cis configuration because both the bromine and the ethyl group are oriented up relative to the carbon we're bonded to. So we have created the cis stereoisomer in both of these cases. Ring flip is always going to maintain the cis-trans stereochemistry, so cis has stayed cis. And now we can ask ourselves that question that we did up top about which of these is more abundant within a container. And looking at these two structures, in the structure on the left, both of the bulky groups are axial. That's not particularly stable. If we look at the structure on the right, lower side, both of the groups are equatorial. That's going to be very, very stable. So this is super low in energy. And therefore, it is definitely going to be the preferred conformation of these two chairs. So this is going to be the more abundant. We could ask ourselves the question of which is going to be more stable, the cis stereoisomer of 1-bromo-3-ethyl cyclohexane or the trans version, because sometimes when we synthesize organic molecules, the reaction will have options of yielding the cis molecule or the trans molecule. And sometimes one of those molecules can be more favorable in the reaction to be yielded than the other because of the fact that it will be more stable overall. So we can ask ourselves, which of these molecules is the most stable overall of the 4 different structures that we drew? And the one that's going to be the most stable overall is the one that's going to have the most groups and the bulky groups in the equatorial position. So of the 4 structures that we've drawn in total, the lowest energy overall of all 4 structures is going to be this one that is in the lower right, because that has all the groups in the equatorial position, both the bromine and the ethyl group. So that's going to be the lowest energy of all the possible different stereoisomers that we can make for 1-bromo-3-ethyl cyclohexane. Considering both cis and trans and the different conformers, this is going to be the lowest in energy. To wrap up this discussion of cis-trans stereoisomers, I want to draw to your attention that there is a shorthand way of representing whether 2 groups that are bonded to a molecule are cis to one another or trans to one another, because it's not always the case that you would necessarily want to know exactly what conformer you were dealing with by drawing out the chair conformations and showing the ring flips and things like that. Instead, you might just be interested in what is the orientation of one group relative to another within the molecule. In other words, are those 2 groups always going to be cis to one another, or always going to be trans to one another, no matter what ring flip you've done? Because remember that the ring flip is never going to change the cis-trans stereochemistry. So a shorthand way or a line angle way of showing cis-trans stereoisomers is if we just want to show whether 2 groups are going to be cis or trans to one another, we can show that using wedges and dashes. So we can show cis-trans stereochemistry with wedges and dashes without having to necessarily draw out the complete chair conformations. So we're going to show cis-trans using wedges and dashes. And we need to define formally what we're referring to when we talk about a wedge or a dash. When we talk about a wedge, what we're referring to is a bond that is pointed toward you. So it's a bond coming out of the page facing toward you. It's as if I'm reaching my arm out toward you. So a wedge faces toward you, it reaches out of the page. On the other hand, a dash is our way of showing that a bond points away from you. So it's showing that that group faces away. When we're trying to show whether 2 groups are cis to one another or trans to one another, if we show the 2 groups both as these so-called dashes, that's going to indicate that the 2 groups are cis to one another. If we show them both as wedges, likewise, that's going to show that the 2 groups are cis to one another. And if we show one as a wedge and one as a dash, that's going to indicate the 2 groups are trans to one another. A dash we represent as a dashed line. So if we had a carbon atom and we show a dash coming toward it, you'll notice that dash gets smaller and smaller, indicating that that group that's bonded there, and we'll call the group R, is getting further and further away from you. It's facing away from you. On the other hand, a wedge indicates that the group points toward you, and that's going to be indicated with this wedge shape that's filled in typically, where the R group there, the generic group that I've pointed out there, is pointed toward you. It comes out of the page. So let's take a look at incorporating these wedges and dashes into cyclohexane structures. So we can draw cyclohexane as a line angle formula or a skeletal formula, like so, our 6-atom ring. We can plug in a group here coming off as a wedge, and we can fill in what we want here at the end. So I'll put an isopropyl group on there to keep that as a line angle formula. And then at position 3, for example, we could put a methyl group. And the point of this drawing is to illustrate that the 2 groups that we've drawn, we would describe, regardless of whatever they are in terms of their identity, they're related as cis to one another because both branches toward them are shown as wedges. So those 2 groups are cis to one another. Also, we could describe a molecule as being cis, or the 2 groups as being cis relative to one another, if we'd put both groups as dashes. So we could show an isopropyl branch as a dash, a methyl group as a dash, and we would still describe the relationship between these 2 groups as being cis to one another. On the other hand, if we put one of those groups pointed forward as a wedge and the other pointed backward as a dash, we describe the molecule as having the trans stereochemistry, the trans relationship between the 2 groups. So we could do that for the isopropyl, pointing that forward, come over to the methyl group and point that backwards. And since those two bonds go in opposite directions, one pointed toward us, one pointed away from us, we would describe that molecule as being trans. So this is a shorthand way of showing whether two groups are cis or trans to one another within a molecule. It can save you a lot of time over drawing out those full chair conformations each and every time. If the point of what you're drawing is just to assign that two groups are cis to one another, two groups are trans, this is the way to do it. In the next unit, you'll get some extra experience at solving problems related to cyclohexane derivatives by going through some example problems, so stay tuned for that.